Our next presenter is Tema Telewo, a Ph.D. student in computer science. Tema's presentation is Garbage In, Gospel Out, Detecting Anomalies in Weather Sensor Networks. Please join me in welcoming Tema to the stage.
Thank you, Eric, and thank you everyone for making time to attend my talk today. As Eric said, my name is Tema Telewo. I work on anomaly detection in weather sensor network. Before I start my talk, I would like to ask you a simple question. How many of you check the weather forecast at least once a week? Almost everyone, thank you. We use weather prediction in daily life all the time. Most of us check the weather app in the morning to decide what to wear. Airline companies and air traffic controllers are looking at the weather to plan flights. Another major application is agriculture. Accurately predicting weather is critical for agriculture in most parts of the world. Africa leads the chart in this, where more than 95% of the cultivated land relies on rainfall for irrigation. Latin America is not so far away, with 90% of the farmland sustained by rainfall. And this is 60% in South Asia. It is therefore critical that we accurately predict the amount of precipitation to allow farmers to know when to plant crops, when to harvest them, or when not to. The way we predict weather is using a sensor network. Here is an illustration of a sensor network. You can look at them as a team of weather watchers that are strategically placed to observe the atmosphere. They track measurements such as atmospheric pressure, relative humidity, solar radiation, and most importantly, precipitation. Do you remember the continent in the world that needs agriculture the most? That needs rainfall the most for agriculture? That's right, it's Africa. But it's ironic because Africa is also the continent that has the worst sensor coverage in the world. That's a major gap. Our goal is to fill this gap and make Africa the continent with the best coverage. The project I'm working on is the Trans-African Hydrometeorological Observatory Network, or TAMO. We currently have about 1,000 weather stations distributed across 22 countries. Our goal is 20,000 weather stations, and this is to cover the entire African continent, 54 countries. For us, precipitation is the most important of the variables, but it's also the most challenging and the most complicated one. The reason is, the problem with precipitation sensor is that they get clogged, and they start reporting zero precipitation even on rainy days. That's the problem. This is because the issue is, in most of the days, we expect zero to be the correct value. For example, in the country of Namibia, it is dry 300 days a year on average. This tells us that when our sensor was saying that it was dry, it's accurate most of the time. However, when it is dry, those sensors get dirty, and then they get clogged. So when it starts raining again, they are still reporting zero precipitation. That's an anomaly. Here is an example of a precipitation sensor. What you see on the left, we have a rain funnel at the top that collects water when it rains. And that water drips down the hole that you see in the middle, and as it falls in the bucket that we see on the right, there's a drip counter that measures the amount of precipitation. This is what it looks like when such a sensor is blocked. Now the question is, why do we care? Why does it matter? The answer is simple. The way we predict future weather is using present and past data. If our data is inaccurate, our prediction will be wrong. So we need to be able to detect those anomalies. And the question is therefore, how do we find those clogged sensors? How do we detect them? That's what I'm working on. That's my project. Going back to our illustration, suppose sensor A is not working correctly. We want to be able to detect it, and quickly, so we can fix it. The way we do that is using machine learning. We have data from the past at some of our stations and their neighbors. So we know that that data is clean. So we are using that data along with the nearby stations to build a computational model of the working behavior of each sensor. Now, when our sensors are reporting the data every day, we can feed those data into our models to predict what is the amount of precipitation we expect. So let's say if we have sensors in Albany, Eugene, we can use them to predict what we expect to see in Corvallis as precipitation. Now, we compare the prediction that our model has produced with the observed value that our sensor has collected. When there is a discrepancy, then we know there is probably an anomaly there. The question becomes, how do we know that our system's detected anomaly is correct? How do we know that they are not lying to us? The way we do this is by using data to evaluate how our model is doing. Here is an example of precipitation collected at one of our stations over 1 year. So what you see on the vertical axis is the amount of rain. On the horizontal axis are the days of the year. So what we do is we simulate a blocked rain gauge, or we add synthetic anomalies by changing some of the days where there was precipitation into zero. That's what the yellow part of the graph is highlighting. Now the question is, we know that we added those synthetic anomalies, but we want to know how good our models are at detecting those anomalies. Suppose the anomaly starts on day 100. So suppose that the sensor was working correctly until day 100, and then it got clogged. If our model detects that there was an anomaly on day 80, that's a false alarm, because on day 80, the sensor was still working correctly. It could be a big problem, because every time our system raises an alarm, we want to fix it. So we have to send the technician to the field to go and inspect the sensors. When you have a network of 20,000 stations, you don't want to have a lot of false alarm. It is very expensive. However, on the other hand, if our sensor says that anomaly started on day 110, then we have a 10-day delay. We don't want that either, because the 10 days that the system failed to detect, we're having garbage data in our system. We don't want that. So our goal is to be able to detect anomaly with very short delay and also very false positive. Now, I hope that when I'm talking to you again in a few years, we have our 20,000 weather stations working correctly and reporting reliable data. And then the continent that right now needs rainfall the most is the continent with the best weather sensor infrastructure in the world. And our farmers in Africa are able to take the predictions that we make as gospel, thanks to our anomaly detection systems that help us detect garbage sensors and produce reliable data. Thank you. Thank you.